Rishikesh. The topic of her talk is from Pingala Prosody to the Fibonacci sequence and its modern application.
Should
Now
I
over
start?
to you.
Should I start?
Yes, ma'am.
My PPT is visible to you?
Yes, ma'am.
Okay. So hope I'm audible also. So thank you, Richa. And I am also thankful to Mrinal and everyone associated with the ISQGD and session coordinators, Richa and Swapnil. I'm thankful to both of you. Today I'm going to speak on from Pingala's prosody to the Fibonacci sequence and its modern applications. Richa, am I audible?
Yes, ma'am.
Okay. So Fibonacci sequence is a fascinating numerical pattern observed in various natural and human-made phenomena like art, architecture, music, plants. So in this sequence, what happens that each number is the sum of the two preceding ones. Although the sequence is named after Leonardo Pisano Bigolo, but it is commonly known as Fibonacci sequence. Its origin can be traced back to ancient India around 200 BC, where it was described by scholar Pingala. Pingala was an ancient Indian scholar and he introduced this sequence in 200 BC. So today we explore the historical evolution of Fibonacci sequence from its early beginning in India to its global recognition, along with the modern day application in cryptography, trading, the stock market, music, and many more applications. So we know that the Fibonacci sequence is 1, 1, 1 and 2, 3, 2 and 3, 5, 3 and 5, 8, 5 and 13, and so on. In this, nth term is given by Sn equal to Sn minus 1 plus Sn minus 2, where n is greater than 2. And here S1 is 1 and S2 is also 1. And this sequence did not originate with Leonardo Pisano Bigolo, and Fibonacci was the nickname of Leonardo Pisano Bigolo. But this sequence originated in ancient India. The foundational idea behind this sequence emerged from the Sanskrit prosody, particularly in the study of metrics, syllables, and morai or matra. In ancient India, learning was experiential and largely oral. Sanskrit, due to its precise structure and phonetic richness, served as an ideal medium for the transmission of knowledge. Consequently, various disciplines, including science, mathematics, and philosophy, were encoded in poetic verses preserved through the Vedas, Puranas, and Shastras, both in written and oral forms. So, these poetic compositions followed metrical patterns known as chandas. Chandas or Sanskrit meters were rigorously studied and classified into three principal categories: Vanvrata, Matravrata, and Ganvrata. Vanvrata means meters in which the number of varnas is fixed, while the number of matras may vary, like in Shakti and Savaya. In Matra Vrata, meter in which the number of matras remains fixed and the number of varna may vary, like in Doha and Chapai. And in Ganvrata, meters based on groups of matras such as Arya and Vatali. So in Ganvrata, there are 8 types of Gana, each comprising of a fixed sequence of matras like Yagana, Ragan, Tagan, Bhagan, Jagan, Sagan, Magan, and Nagan. You can see that each Gana maintains a constant number of matras while the number of letters in the group may vary. Like here is it 122, 212, 221, 211, 121, 112, 222, 111. In the context of Vanvrata, the number of possible variation increases exponentially with the number of syllables. A meter with one letter Varna has two variations. Laghu, Laghu means short and we represent it by L. And Guru, Guru means long and we represent it by G. A meter with two letters has four variations. And meter with three letters has eight variations. If we continue this process, in general, the number of variations of for a meter with n letters is 2 raised power n. So clearly this expansion follows a recursive method. To generate all variations for a meter of length n, one takes each variation of length n minus 1 and appends both a laghu and guru to the left. Hence the total number of variations becomes 2 raised power n. You can clearly see in this table that for one letter there are two variations G and L. For two letters there are four variations. One is GG, LG, GL and LL. There are four variations. We can write in four ways. For three letters, there are eight variations like 3G or LGG or GLG or LLG, GGL, LGL, GLL and all three L. And we continue the process. For n letters, there will be 2 raised power n variations. And expansion in Matra Meru maintains a fixed number of matras. Here Laghu represent one matra and Guru represent two matras. So one matra means one variation means it is Laghu. Two matras means two variations. Two variations means it may be Guru. Guru means two. Or it may be Laghu, Laghu means one and one. Together it will be again two. In three matras, there will be three variations like there may be one Laghu and one Guru means one and two, three. Guru and Laghu, 2 and 1, 3, or there may be 3L means uh, 1, 1 and 1. So 3 Laghu means again 3. For 4 matras, we have 5 variations. 4 means 2 and 2, G, G. 4, L, L, G, 1, 1 and 2, 4. L, G, L, 1, 2 and 1, 4. GLL 2, 1 and 1, 4 or for 1, 1, 1, 1. So 4. So for 4 matras, we see that we have 5 variations. And for 5 matras, we have 8 variations like this. So Pingala was an ancient Indian scholar from around 200 BC. He was the first to systematically study chandas. Chandas are Sanskrit meters using a mathematical approach. In his seminal work Shastra, also known as Pingala Shastra, he analyzed meters based on sequence and arrangement of Laghu. Laghu means L, short syllables, and Guru means long syllables in verses. His work laid the foundation for the combinatorial analysis of metrical patterns in Sanskrit prosody and music. Just as basic unit of mathematics is the number, the basic unit in Sanskrit prosody are syllables of one or two morai. Morai means matras. So we have seen that Laghu is a short syllable with one matra and Guru is a long syllable with two matras. So in the combinatorial framework, L and G plays a role analogous to the integers 1 and 2 respectively. Pingala's exploration of the number of metrical combination with a given number of syllables directly correspond to the principle of binary enumeration and forms an early example of discrete mathematics. So in Chand Shastra, Pingala described binomial coefficients, the structure of what is now known as Pascal's triangle, the recurrence relation of the Fibonacci sequence. So his analytic methods allowed poets and scholars to determine how many distinct metrical forms could be constructed from a fixed number of syllables using combination of long and short syllables. So this problem that how many different meters can be created from n syllables using varying patterns of Laghu and Guru was elegantly addressed by Pingala and later elaborated upon by his 10th century commentator Halayuddha. So in ancient India, chandas were closely associated with the music due to the rhythmic and melodic structure of poetic verses. There was one more thing important, that during ancient India, the knowledge was transferred from one person to another in the form of uh, in poetic version. It was not a written; it was transferred in the form of chandas or dohas. Music in that era was broadly characterized into three types: Swar Sangeet, Varn Sangeet, and Tal Sangeet. Swar Sangeet is based on uh, intonation, focusing on tonal quality and pitch. Varn Sangeet was based on long and short syllables. Varna, which is used to compose metrical lines, where each syllable, Laghu and Guru, served as a time unit. And Tal Sangeet was based on rhythmic patterns, where music is composed with structured voice modulation and recurring beat cycles. So initially, Swar Sangeet formed the foundation of musical composition, where the passage of time was not defining factor. However, with the evolution of musical expression, Varna Sangeet emerged, placing emphasis on the duration of syllables. So this evolution raised the fundamental question that how many meters can be formed using and syllables composed of Laghu and Guru. So his in analysis of Sanskrit meters, Adyanta and Adyanta and Upajyanta is a specific class of meter where the beginning and the ending syllables are mixed while the intermediate syllables vary. And Halyudha commentary on Pingala Chandracha, he write a Sanskrit version like this. It means the initial and final parts is Adyanta of the meter must be either completely in the form of Indravarja. Indravarja means all gurus, and Upendra Varja means all laghus. So the syllabus in between can be formed by mixing these two in any desired member as described in the expansion of Prastha. So Indra Varja composed entirely of gurus and Upendra Varja composed entirely of laghu syllables. For a metric composition of n syllables, the central part, excluding the fixed beginning and ending syllables, can be formed by all possible combination of GLN. So this gave rise to a metrical expansion of the form L plus G raised to n, which is central to the Pingala's combinatorial method. So from the foundational rules given by Pingala and elaborated by Halyudha, the expansion process can be summarized. Begin with the line containing only Guru syllables, replace the first Guru with Laghu, keep the rest as Guru. Continue this process iteratively by converting one additional Guru to Laghu from the left at each step. Fill all preceding positions on the left with Guru until the entire line becomes Laghu. For example, for a meter of one syllable, there are only two possible patterns, G and L, the two extreme cases. For two syllables, there are four possible patterns like this, including intermediate mixed forms. So this pattern of expansion generalizes to any n syllables and correspond precisely to the binomial expansion. To determine the number of combination each phase of expansion, Pingala introduced the concept of Meru-Prastha, which is mathematically identical to the Pascal's triangle. So the prastra of a meter for one syllable is like this. This I have explained in earlier slide also. So if the variations are G and L, this is equivalent to G raised to power 1 and L raised to power 1. And this gives the combination L plus G raised to power 1. 1 and 1, the syllable 1, there are no intermediate or mixed term. It has only two extreme values. For two syllables, there exist two intermediate terms existing of mixture of Guru and Laghu, like GG, GL, LG, and LL. So we can write like this: G square, GL, GL, and L square. So this is the expansion of L plus G whole square, and the binomial coefficients are 1, 2, and 1. Here we have two Guru, here one Guru, and here no Guru, means zero Guru. So G square, 2LG, we have added these, and L square. For three prastha meters for meters of three syllables, we have these variations which are equivalent to this, and we get the expansion of L plus G whole cube, where the binomial coefficients are 1, 3, 3, and 1. And for 4 syllables, this is the variation, and this is the expansion L plus G raised to power 4, and the binomial coefficients are 1, 4, 6, 4, and 1. So each row in the Meru Prastha represents the binomial coefficient for the expansion of L plus G raised to power n, indicating the number of ways each metrical variation of n syllables can be constructed. So Hal Yuddha further explained the sutra related to this expansion, reinforcing the deep connection with Sanskrit prosody and mathematical combination. So this illustrates not only advanced metrical science of ancient India, but also its significant contribution to the foundational principle of binary system combinatorics and what we now recognize as the Fibonacci sequence. So this method is applied for n number of syllables, which will be given as an expansion of L plus G raised to power n. So to determine the binomial coefficient in the expansion of Pingala, gave his general rule called the Meru Prastha, exactly similar to the Pascal triangle. So Halyuddha explained the sutra as follows. So I will explain this with the help of triangle, means Matra Prastha. First of all, we construct squares, means initially we construct one square. Below one square, we construct two equal squares. Then in between, we construct 3 square, then 4, then 5, then 6, and so on. So on the extreme left, we write 1. And in between, we write the sum of these two. So 1 and 1 is 2. 1 and 2 is 3. 2 and 1 is 3. Here 1 and 3 is 4. 3 and 3 is 6. 3 and 1 is 4. So here 1 and 4 is 5. 4 and 6 is 10. 6 and 4 is again 10. 4 plus 1 is 5. 1 and 5, 6. 5 and 10, 15. 10 and 20. 10 and 5, 15. 5 and 1, 6. So this is how we form this Matra Meru of Pingala. You can see that these are the binomial coefficients, and this is easy way to get the binomial theorem, and this is also called Pascal triangle nowadays, but it was given by Pingala a way back. If we add them diagonally, means this is 1, again this is 1, 1 and 1, 2, 2 and 1, 3, 1, 3 and 1, 5, 1, 4, 3, 8, 1 and 1, 5, 6 and 1, 13. So if we add this term diagonally, what we get? 1, 1, 2, 3, 5, 8 and 13 and so on. So this is nothing but the sequence which we call today Fibonacci sequence. So we can see that some of the diagonals gives a sequence which is similar to the Fibonacci sequence, and if we calculate the ratio between two consecutive terms, it will tend to 1.61, which is the golden ratio. Today we call it golden ratio. So all this was given by Pingala. After this, Virhanka was also an eminent Indian scholar of prosody and mathematics. He lived approximately between 6th and 8th century CE. He built upon the foundational Shastra of Pingala and significantly extended them. His work formed the basis of later commentaries by scholars such as Gopala and Hemachandra. So Virhanga is notably recognized as the first to formally articulate the recurrence relation, now famously known as the Fibonacci sequence, in his Prakrit test Varta Jati Samuche. While Pingala's metrical framework was largely centered on the Varnvrata, Virhanka's innovation was based on Matravrata metrical pattern, where the total number of morai remains fixed and the number of syllables can vary. So this shift provided a deeper combinatorial insight into rhythmic structures. In Matravrata, Laghu means one matra, Guru means two matra. So Virhanka's key contribution lies in formulating a recurrence relation for enumerating all possible metrical patterns of a given total number of matras. So this relation is called uh, is mentioned in the following work of Virhanka's theorem in Prakrit, and this is his Sanskrit translation. It means each subsequent number is obtained by combining the previous two. This gives the number of total patterns for a given number of matras. So mathematically, this is equivalent to the Fibonacci recurrence relation, and thus the number of rhythmic combinations of matras follow the pattern of Fibonacci sequence. So Virhamaka's formulation centuries before Leonardo Pisa demonstrate how ancient Indian metrics encoded sophisticated mathematical principles, including combinatorics and recursion in poetic and linguistic frameworks. So this is the proof of his theorem. I'm skipping that because uh, we have less time. So this is the explanation given by the Viranka for his work. This is all about the explanation of Virhanka. So here I want to mention that if we isolate the process reveals a hidden recursive structure that involves not only summing consecutive terms but also forming values through multiplication and subtraction, suggesting deeper algebraic and combinatoric symmetries. If we isolate the subtracted values used in the above rule, like 0, 1, 1, 2, 3, 5, 8, 13, 9, 21, we obtain the same Virhanka Fibonacci sequence again. Interestingly, if we reverse the sign of these subtracted values, 1, 0, -1, -2, -3, -5, -8, -13, and so on, we again derive a variant of Virhanka sequence, revealing that both additive subtractive transformation maintain internal consistency with the original structure. So we can define further generalized sequences in the form Sn equal to Sn minus 1 into n plus Sn minus 2 minus n, and we get the sequence 1, 2, 3, 5, 8. So this expression simplified to another sequence of the form 1 minus n, 2 minus n, 3 minus 2n, 5 minus 3n, 8 minus 5n. Each term combines linear growth with variable offsets that encode differences similar to earlier Vihanka rules. This suggests that multiple layers of combinatorial arithmetic lie embedded in these ancient prosodic sequences, revealing profound insights in early Indian mathematical thinking. So this was all about the Virhanka. You can see that if we take the ratio of two consecutive terms, we tend to golden ratio. After Virhanka, the work of Gopala was based on Matravarta rule given by Virhanka around 600 AD. He specifically mentioned the number of variations of Matravarta while commenting on the Virhanka theorem and rules in Vritajati Samuche. Proof of commentary is found in the form of handwritten palm leaf manuscript. It is available in Jaisalmer, Rajasthan. A detailed explanation of Vihanka rule is given by Gopala. Variation of Matravata is given by variation of two earlier meters. So the Fibonacci sequence, widely known in modern mathematics, is attributed to Italian mathematician Leonardo Pisano-Vigolo, popularly known as Fibonacci, who introduced it in his work Liber Abaci in 1202 AD. The sequence was used to model the growth of rabbit population under idealized condition. The classic rabbit problem, the Fibonacci posed the following problem. This is the page of the Liber Abaci from the National Central Library. The list on the right shows the numbers which are nothing but Fibonacci sequence. The 289 resemble Arabic numerals more than Eastern Arabic numerals or Indian numerals. So this is the rabbit problem. We begin with one pair of newborn rabbits, male and female. Each pair becomes fertile after 1 month. So after 1 month it is the same. Each month a fertile pair produces one new pair which become fertile from the next month. So it gave birth to, this pair gave birth to this. No pair dies and reproduction continues. So again this pair gave birth to this. So we get 3. This pair gave birth to this pair gave birth to this pair. So we get 5 pairs. Then again next time, this is we get 8 pairs. So we observe that in first month we have 1 pair, no production, no reproduction. In second month we have 2 pairs, original pair reproduces. In third month we have 3 pairs, one original pair plus one new pair from previous generation. And month 4 we have 5 pairs. So the nth month population is the sum of populations from the previous 2 months. So number of pairs at the end of nth month is the number of pairs in n minus 2th month plus the number of pairs alive in the n minus 1th month. So this yields to the now familiar recursive sequence fn equal to fn minus 1 plus fn minus 2 with seed values f naught equal to 0, f1 equal to 1 and greater than 1. So this recursive formulation is identical to the developed independently by Virahanka, Gopala, Hemchandra in India centuries early using metrical patterns in prosody in Indian tradition. So this is the closed solution form solution and the golden ratio. The Fibonacci number also admit a closed form expression known as the Bennett's formula. These are the Bennett's formula, and the ratio is the golden ratio. So we have applications of Fibonacci sequence in cryptography. I am not explaining these slide by slide. We also have application in trading. We also have application in music because the historical roots of Fibonacci sequence trace back not in European methods but to the rich tradition of Indian music and poetry. The sequence known in India as the Virhanka sequence was first formulated in the context of Matra Chanda, metrical pattern of syllables used in classical Sanskrit prosody. Scholars such as Pingala and later Vihanka, Gopala, and Hemchandra explored how combination of Laghu and Guru syllables could form metrical patterns, which are essentially rhythmic compositions. In Indian classical music, rhythmic cycles, tal, are composed of beats. The beats are often vocalized using mnemonic syllables like dha, one beat, matlab laghu, thir kita, dhindha, two beats means guru. Thus, using combination of one beat and two beat syllables, one can generate multiple rhythmic combinations. For instance, for n equal to 5 syllables, the number of possible variation using Laghu and Guru correspond to Virhanka number. S5 means 8. 1, 1, 1, 1, 1, 1, 5. The 3, 1 and 2, 5. 3, 1 and 2, 5. This is again 5. This is again 5. So hence 8 unique rhythmic patterns can be composed from 5 total syllables. Below are 8 valid rhythmic combination of 1 beat and 2 beat using 5 beats. So this is LGG means dha thir kita. LGL means thir kita dha thir kita and so on. So each of these correspond to distinct rhythmic rhythm using Indian percussion syllables. Thus, the mathematical structure provided by Viranka sequence is directly applicable to composing rhythmic complex music, especially within the Indian Tal system. Interestingly, Fibonacci relationship also appear in Western classical music. The piano keyboard has 13 keys in an octave, 8 white and 5 black, arranged as 2 plus 3. The violin and other strings instrument also often designed with proportion based on the golden ratio. Musical phrasing and timing in composition often exhibit patterns based on Fibonacci number or golden means division. The Fibonacci sequence, far from being purely modern or mathematical curiosity, is deeply embedded in the musical heritage of humanity. Originating from Indian metrical theory, it continues to influence the way we understand and create rhythmic structures across cultures, instruments, and eras. So again, we have many more applications of Fibonacci sequence. These are some modern applications which we have used. This is actually, these fractals are from my paper. So we have combined Fibonacci sequence with Mann iteration, and we introduced Fibonacci Mann iteration to obtain these fractals, and generalized Fibonacci Maya iteration with an S convexity to visualize aesthetic fractals. So these are the fractals we obtained. This paper is published in Chaos Soliton and Fractals and other journals of international reputes. In this, we have used Fibonacci sequence. So in short, we can say that the Pingala introduced a combinatorial framework of binary syllabic meters using Laghu and Guru. He generated patterns akin to the Fibonacci sequence, referred to as Matra Meru. Virhanka explicitly formulated the recurrence relation giving the sequence, which is known as Fibonacci sequence. Gopala further provided commentary and elaboration of Rehanka's method for enumerating Matra Vrata. Acharya Harchandra independently described the same recurrence in his treatise. Narayan Pandita continues this tradition, extending the sequence to more general combinatorial settings. So, the remarkable resemblance between the Fibonacci sequence and the earlier Vihanka sequence is not coincidental, but a testament to depth of mathematical thought in ancient India. The neglect of Vihanka's priority and Pingala's foundational role in Western historiography highlights the need for corrective revaluation. Therefore, we propose that the sequence commonly known as the Fibonacci sequence should be more appropriately be referred to as Fibonacci Prehanka sequence or more inclusively Pingala Prehanka Fibonacci sequence. So, this nomenclature would acknowledge the independent and earlier discoveries in India, honor the text, original context in Sanskrit prosody and combinatorics, encourage a more inclusive view of global mathematical history. Such a renaming would not only give credit where it is historically due, but also serve as a symbol of intellectual continuity and cultural contribution across civilization. So these are the references which we have used in making this presentation. Thank you.
Thank you, ma'am, for the nice talk. Let me stop the recording.